Okay, so in last lecture, we were solving some problems uh, to find the Lagrangian basically, and then oh no. And we consider simple pendulum and then double pendulum, and today again we will consider some examples such that you know how to calculate Lagrangian. So let me share my screen. Okay. Yeah, so last year the example we considered that uh, just a moment, it's not writing pen happened. Okay. Okay. What is the wrong? Something is wrong. I don't know. Okay, so we consider yes, there is some difficulties in my pencil. I don't know. Hmm. I charge my battery, but pencil, but I don't know. Let me try again. So we'll consider. So you have to learn how to construct Lagrangian. This is the main part of classical mechanics. Once you know for any problem you can construct a Lagrangian, then you know half of the classical mechanics. The rest of the thing is that finding equation of motion and then solving the equation of motion to find the dynamics. So we'll consider more and more example, and we'll give you in the assignment also more examples such that you learn how to consider uh, how to calculate Lagrangian for a system. I have little bit difficulties in my pencil. I don't know why it is not working. So let me. I charge it in the beginning, before the class, but okay. Now it is working. So let me. So so we consider that there is a pendulum, and then another pendulum is attached. So so then we calculate the Lagrangian. So Lagrangian, so if this is L1, this mass is M1, this is L2, this mass is M2, and we also find that it is always convenient to describe in terms of
सर
angle of
सर
angle of हाँ.
सर
Yeah,
सर मिड सेमेस्टर कब होगा सर इसका कुछ पता है क्या?
department will tell you. So once department will give you the notice, you'll know.
नोटिस आएगा ना सर उसके लिए?
हाँ हाँ, क्यों नहीं, बिना नोटिस कैसे आपका एग्जाम होगा? स्टूडेंट कैसे आएगा खुद, है ना? आप लोग
ओके
थर्ड फिफ्थ सेमेस्टर में है आपका, पता होना चाहिए, अभी हो सकता फर्स्ट सेमेस्टर में आप लोग मिड सेम तो दिया था. So this theta 1 and theta 2, then you know the kinetic energy minus potential energy. So total kinetic energy for first particle, which coordinate, if you assume the coordinate as x1, y1, and this coordinate is x2, y2. This is my x-axis. This is my this is my y-axis, and this point is 0, 0. I am taking u equal to 0 around this point, so then I have kinetic energy. So half m1 x1 dot square plus y1 dot square minus mg y1. This is for first particle, and the second particle half m2 x2 dot square plus y2 dot square minus m2g y2. So this will be my Lagrangian, and without assuming the constant, but the system has constant. Constant is that the length of this pendulum, first pendulum L1 is a fixed quantity. Similarly, length of the distance from the first mass to the second mass, so length of the second pendulum is also fixed. So that constant equation, if we write, so x1 square plus y1 square, making the triangle L1 square, then x2 minus x1 whole square plus y2 minus y1 whole square equal to L2 square. So these are the two constants. So you can make them in terms of angle variable, keeping that this
सर
triangle. हाँ
सर जो पोटेंशियल एनर्जी के लिए जो सर एक्सप्रेशन लिखा गया है वो सर जीरो पोटेंशियल कहाँ पे लिया गया है इसमें?
लिखा है ना, आप कहाँ सो रहा है क्या? इसी पिक्चर में ही लिखा है और हमने बताया भी गया है. तो आप कहाँ क्या कर रहा है? फोन ऑन करके आप सो जा रहा है क्या?
नो सर
अब
उसमें
देखो, नहीं
मतलब
देखो इस पिक्चर में दिखाई दे रहा है कि कहीं लिखा है कि नहीं?
सर दिख रहा है सर, लेकिन जब नीचे आएगा तो सर वो माइनस रहेगा ना, इसमें
हाँ तो
प्लस लिया गया है।
हाँ तो वो सवाल आप पूछ सकता. तो ये y1 को हम लोग माइनस y1 मान रहा है, तो ये
हाँ
सवाल
हाँ
आप.
वही
हाँ
वही
तो
पूछ रहे थे सर,
हाँ,
मतलब
तो
जो
आपको क्वेश्चन गलत पूछ रहा है ना, तो आप बताए सर ये साइन प्लस होगा,
सर
तो हम
हमको
तुरंत मान
दिखा नहीं
लेंगे
है
कि.
सर, किनारे सर मोबाइल पे मतलब u इक्वल टू जीरो दिख नहीं रहा था, तो हमको लगा सर इसलिए हमने
बताया
पूछा
भी
पहले।
तो, दिख नहीं रहे तो बताया भी तो. आप ऐसा सवाल पूछोगे तो क्लास डिस्टर्ब होगा. जो हमने बताया लिखा है उसका बाद आप पूछ रहे हैं. हाँ तो ये करेक्ट कर लीजिए कि हमने इसी को y डायरेक्शन मान रहे हैं, तो नीचे माइनस पोटेंशियल एनर्जी होगा, तो ये माइनस वाई टू होगा, तो ये साइन प्लस होगा.
यस सर।
तो हाँ तो इसको एंगल का टर्म्स में आप लिखिए, जैसे L1 x1 is this distance. So if this distance is x1, this is theta, so it will be L1 sin theta, theta 1. Similarly, y1 also will be L1 cos theta 1, and x2 minus x1, because if you take this red line distance will be x2 minus x1, so it will be L2 times sin theta 2, and y2 minus y1 equal to L2 cos theta 2. So then if you substitute this in this Lagrangian, then you will get a Lagrangian purely in terms of theta 1 dot, theta 2 dot, theta 1 and theta 2. So this system has 2 degrees of freedom, and I must have 2 generalized coordinate, which is theta 1, theta 2. So if you ask to find the Lagrangian, you have to find the Lagrangian with in theta 1, theta 2. If you write the Lagrangian up to this is not the correct Lagrangian, because in this Lagrangian we have not considered the constraint, the motion in a plane. So 2 to 4 dimension we have written. So okay, so you have to substitute and then you have to write this Lagrangian. Because of algebra, I'll not write this Lagrangian for you. You do yourself. and find equation of motion. So what will be this Lagrangian and equation of motion? There will be two equation of motion, one for theta 1, another for theta 2, that you have to find from this Lagrangian. Okay. So this I taught last time, so I'm not doing in details. So once you find this Lagrangian, the theta equation of motion, then you will find it will be a coupled differential equation which is difficult to solve. You may not able to solve this equation because it will be a coupled differential equation. Coupled means when you have theta 1 double dot will mixed with theta 2 variable. Okay. So this will be a coupled differential equation and you will not be able to solve. But in a special case, so now we are going to tell you that special case. Let us consider that L1 equal to L2 and M1 equal to M2 equal to M. So we assume that both the length are same. We also assume that both the mass are same, and we substitute in this equation of motion. So these two things you have to do. One is that find the Lagrangian in terms of theta 1, theta 2. I wrote x1, x2, y1, y2. You have to find in terms of theta 1, theta 2. Then you put L1 equal to, this is a special case. Then you will find a equation which I'll write for you, but I'll not solve it now. Let me write this equation. So I can write this equation such that you can verify your calculation. So let me write from my notebook. So you will get two coupled equation. Again, it will be coupled, but this coupled differential equation can be solved. 2 theta 1 double dot plus theta 2 double dot plus 2 g by L theta 1 equal to 0. And second equation you will get theta 2 double dot plus theta 1 double dot plus g by L theta 2 equal to 0. Of course, you have to assume that small oscillation approximation. You have to small oscillation means theta 1 is very theta 1, theta 2 are small. That means the oscillation, this angle is cannot be large, such that you can make this approximation. Sine theta 1 is approximately theta 1, sine theta 2 is approximately theta 2, and cos theta 1 minus theta 2 will be approximately 1, sine theta 1 minus theta 2 will be approximately equal to theta 1 minus theta 2, I think. So this is not needed. I think this approximation, then you get this equation. I'll discuss the solution of this equation little later. Solution will be discussed later once you study the small oscillation. Dr. Krishna is teaching small oscillation. So if you learn those technique, then I'll teach the small oscillation. Yes.
सर इसमें मतलब इसको सॉल्व कैसे करेंगे, इसमें कौन सा तरीका यूज़ करेंगे सर, क्योंकि इसमें दोनों है तो इसको कैसे सॉल्व करेंगे?
नहीं बेटा, आपने भी पहले वही ये वाला पूछा था ना, वो जीरो ऑफ द पोटेंशियल एनर्जी आपने ही पूछा ना?
यस सर।
हेलो, हाँ, तो आपको हमारा व्हेन आई स्पीक यू डोंट अंडरस्टैंड माय लैंग्वेज, मैंने अपने इंग्लिश में आपका कोई दिक्कत हो रहा है कि अभी तो हमने बताया कि आई विल डिस्कस दिस सॉल्यूशन लेटर, हाउ टू सॉल्व दिस आई विल डिस्कस लेटर, or then you are asking me that how to solve this equation. So that is why I am showing that you either you have some difficulties in hearing or you don't understand what I am saying. I said that this solution I will discuss later. This you can do yourself, derivative, x1, x2, x derivative, and then you substitute. Then equation of motion is also Euler-Lagrangian equation, simple differentiation you can find. Then equation you can find. Then I am asking you to use the special case that both length are same and make it L, and both masses are same, make it M, and then you take the small oscillation approximation. So three things you do, and then you will get this equation. So I am asking you to come up to this equation and keep as it is. Solution we will discuss little later. I mean, after a few classes, I'll ask the technique. Some technique is involved, which is supposed to taught by Krishna. If he did, I'll ask him whether if he is not teaching that technique, then I'll tell you the technique. This is called normal mode solution. So he is supposed to teach you how to find normal mode solution. Try to listen to me, and then if you are not understanding, then ask that question. Okay, so this is all about double pendulum. Now you can have many other type of pendulum. So that let us discuss that. So maybe I'll erase. Okay, so now another type of pendulum you can have, many different pendulum you can have, and find the Lagrangian. For example, the similar pendulum, suppose I have three pendulum, L1, M1, L2, M2, L3, M3. You can easily find the Lagrangian in terms of theta 1, theta 2, and theta 3, their derivative. This you should. I'm not going to discuss. Can you see my screen? Hello?
Yes, sir.
No, but triple pendulum, can you see?
Yes, sir.
Yeah, but surprisingly, I cannot see in my laptop. It's very surprising. Okay, so you can see, then it is fine. I wrote a three pendulum, right? You can now I am putting this masses. You can see, right? Okay, good. But what happened to my?
So you should unpin your that slide and then again pin it.
Unpin. Let me. Okay. So Shruti is expert on all this. So unpin. Okay, I have to go to the list of. Okay. Unpin, then pin again. Yeah, it's great. I don't know this technique. Okay, great. So this is the triple pendulum you can solve. So anybody can solve, right? I'm not going to discuss this. So, and then there is another problem. Let us see. There is a mass. This pendulum is connected to a mass, capital M, and then we have simple pendulum connected to small m with length. Now this mass, capital M, is moving in this direction. Suppose this is my x direction, and this mass originally, and this is my y direction. This is my zero of potential energy, this level, and this mass is connected with this small mass with the length. Now I have to find the Lagrangian. So there are two mass. This mass is degrees of freedom. Degrees of freedom, first we have to calculate. This first capital M has degrees of freedom 1 because it is moving only in one direction. Small mass also has degrees of freedom 2 minus 1. It is having a motion in the xy plane. So let me write x1, y1 coordinate at any time. and so it is moving in a two-dimensional plane, but this L is constant, so this degrees of, so total degrees of freedom is 2 for this problem. So let me write the Lagrangian. Let us, at any instant of time, this coordinate of this smaller mass is x1, y1, and this I assume x0. Okay? Coordinate of the capital mass is x0. Okay, so my Lagrangian kinetic energy for capital M will be half m x dot square. Potential energy, Manish Kumar, can you tell us what will be the potential energy of this capital M?
0 लिए तो 0 ही होगा ना सर?
हाँ, 0, very good. तो इस लेवल में हम 0 लिए तो इस will be 0. If I take the 0 somewhere else, it will be at some constant. It cannot depend. Okay. So this is for first particle capital M. Second particle pendulum, as it is half m x1 dot square plus y1 dot square, and u will be minus mg y1. Okay, minus mg y1. So your Lagrangian in this form will be half m x dot square plus half small m x1 dot square plus y1 dot square plus mg y1. Okay, but again I will prefer to this shows that there are 3 degrees of freedom, 1 coordinate, 2, 3 coordinate, but my Lagrangian will have 2 coordinate, 2 degrees of freedom, so 2 coordinate. So I have to again this pendulum, for this pendulum 1 degrees of freedom, so x1, x2 we have to eliminate in terms of some angle theta 1. Yes.
Yes sir.
हाँ,
तो सर
okay.
जस्ट आस्किंग दैट, मतलब सर जैसे इसका लेंथ एल है ना, तो सर इसमें कोऑर्डिनेट्स के बीच में रिलेशन होगा, उसको यूज करेंगे तो भी 2 वेरिएबल में आ सकता है? नहीं
आएगा, क्या क्यों आएगा? हम एक कांस्टेंट जब यूज करेंगे, आप बताओ कांस्टेंट इक्वेशन क्या होगा? इक्वेशन ऑफ कांस्टेंट बताओ।
हाँ
एकदम इक्वेशन ऑफ कांस्टेंट
x1 minus x whole square plus y square equals to l square है।
वेरी गुड।
तो
सो दिस विल बी द कांस्टेंट
हो सकता है, हो जाए।
हाँ, एल स्क्वायर। तो 2 वेरिएबल नहीं आएगा, ये तो इक्वेशन है, तो हम y को एलिमिनेट कर देंगे तो y नहीं रहेगा, x 2 रहेगा लेकिन 3 नहीं रहेगा, x तो रहेगा।
हाँ,
बट x1 एंड y1 में एक एलिमिनेट हो जाएगा इन टर्म्स ऑफ, so this is constant equation, everybody understand, because distance between these 2 points, this point is x0, this point is x1, y1, so distance between these 2 points length should be l square, distance square should be l square. So my constant in terms of theta I'll write, so let me complete this triangle. So this length will be x1 minus x, right? So x1 minus x should be my L sine theta 1, and this distance is my y1, so y1 will be L cos theta 1. So I can substitute my x dot, y dot, and I put in the Lagrangian, and I can get the Lagrangian. So again, it is your job. I have done everything, only thing this differentiation and substitute. So you find a Lagrangian x and theta 1 dot. Okay, 2 variables, 2 generalized coordinate, one is x, another is theta 1, and theta 1 x dot also. So this Lagrangian you can find. Okay, I can make life much more difficult, but your technique, if you follow this technique, finding Lagrangian will be very simple.
Yes sir, I understand.
So for example, now I said that this mass is moving in the x direction. I could have said that this mass is not moving in the x direction, but this mass is moving in the y direction. That also I can give. This mass is moving y direction, pendulum is attached, this pendulum is oscillating. So this is one problem, find Lagrangian. I can say that this mass is moving in a circle circle with radius at the x line. So my circle is wrong. So let me redraw the circle. So I said that this mass is moving in a circle around initial point or around origin. I can say that around origin. I can say that this mass is oscillating in x direction, y direction, or x direction. So all these complicacy I can bring. You can see in the Landau-Lipschitz book, there is in the exercise, this problem is given that this mass is moving in a circle. This mass can oscillate in x-axis. This mass can oscillate in x-axis, y-axis, or anything. Only thing is that you have to see that what plane and what degrees of freedom and what will be the appropriate generalized coordinate. So I leave that problem. I will give you this problem in a assignment problem. Okay. So you can find Lagrangian. Now there is another concept which is called spherical pendulum. Let me tell you the what is the meaning of spherical pendulum and how to find the Lagrangian. After today, we will not consider much example on Lagrangian, but give you problem set and then you can solve those. We have to go for some theory topics and then, okay, spherical pendulum. Spherical pendulum means that this pendulum, by pendulum we means a length and a mass, right? So if this mass, point mass, if this point mass moves on the surface of a pendulum, sphere, moves on the surface of a sphere, radius, that means the point of support, this point of suspension is at the center. Just imagine. And the pendulum is not allowed to oscillate in a plane. Earlier it was in a plane, oscillating in a plane. But now the pendulum is allowed to move in a surface. The mass point can go anywhere in the surface, x square plus y square plus z square equal to a square. This is the surface of the sphere. So that kind of pendulum is called spherical pendulum. So this is definition. Now Lagrangian. So Lagrangian Lagrangian, you have to write the kinetic energy in a this is L. So let me write this L. Okay. So Lagrangian is kinetic minus potential energy. Now I am considering. So this is my sphere and this is my origin. So this is my, say, XYZ axis. I am considering that in this z equal to 0 plane, z equal to 0 plane is the potential energy 0 plane. So that I am assuming. 0 of the potential energy when z equal to 0 plane is then. So my potential energy will be mgz. Any times it will be mgz. If it is z going downward, then z is negative, so it will be the potential energy will be negative. If it is upper side, then so my kinetic energy is supposed to be, I should write this kinetic energy in spherical polar coordinate. So you should remember that it should be half m. Then then let me write L dot square supposed to be, but here L dot square will be 0. L square theta dot square and then L square sine square theta phi dot square. So this is the, but L is fixed here, so this term will not be there. So it will have, and then potential energy is mg. So Lagrangian for a spherical pendulum will be 2 dimension, 2 degrees of freedom. It is a motion in a 3 dimension, but length is fixed. So 2 dimension, 2 degrees of freedom. So remember, this problem has 2 degrees of freedom. So my Lagrangian will have 2 variables, and that is theta and phi. Okay. So this will be half m L square, you can take common, sorry, half m L square theta dot square sine square phi dot square, then
साइन स्क्वायर थीटा होगा वहाँ
exactly theta and minus mg L z equal to L
cos theta.
cos theta. So this, you should not write z here, then there will be 3 variables, theta, phi and z, but z is basically related to L cos theta. So this will be your Lagrangian for a spherical pendulum. And then you find equation of motion, etc. That I'm not doing, but and if it is solvable, then you can find the solution. Okay, so this is all about pendulum. Now I can discuss the other type of problems. So let me write one more problem. There are few problems we can solve. So things are clear to everybody how to write a Lagrangian for this. Okay. Okay. So now suppose I have a particle of mass m. So particle of mass m moves freely. Let me write the problem. On a smooth wire, whose equation, the equation of the wire, whose equation in cylindrical coordinate is given by rho equal to constant, z equal to b phi. Then find the Lagrangian. Everybody understood this problem? Mass m, single point mass m moves freely on a smooth wire. Suppose you have some wire, and the wire equation is given, it is in cylindrical coordinate, rho equal to a, z equal to b phi. So 2 constants, so 1 degrees of freedom. First you understand degrees of freedom is 1. 3 minus 2 equal to 1. Okay. Right.
Yes.
So mass is moving on this wire, and I have to find the Lagrangian. It is very simple problem, but it's a new type, so I am just giving you. So what you have to write, you have to think of in terms of kinetic energy in terms of cylindrical coordinate. This is also the reason of choosing this problem, that it is in the cylindrical coordinate. So kinetic energy in the cylindrical coordinate, half m, then rho dot square, then rho square phi dot square plus z square, z dot square, right? And I am assuming the potential energy u equal to 0 for z equal to 0 plane. Z equal to 0 plane passing xy plane passing through origin, right? So that xy plane is potential energy 0. So it will be minus mgz in general. But now equation for the wire, it is only one dimensional. Wire is one dimensional, so degrees of freedom is 1. So equation of motion is given like this, so that I have to use in the Lagrangian. So what I'll have, this is my Lagrangian. Let me write, this is my Lagrangian. So rho equal to a, so rho dot equal to 0, z equal to b phi, so z dot equal to b phi dot. So I substitute. So my Lagrangian will be half m, then rho is gone. This rho square is a square, then phi dot square, and z square will be b square phi dot square. And then minus mg b phi. So one variable. Everybody see that 1 degrees of freedom, Lagrangian is one variable, phi. So I substitute z equal to b phi and here and here, okay, and rho also so I eliminate 2 degrees of freedom. So my Lagrangian will be half m, then a square plus b square phi dot square, right? Half m square plus b square phi dot square minus mgb phi. And this is very simple Lagrangian. Not only very simple Lagrangian, you can find the solution also. You can this equation find equation of motion and the solution. I'm not going to do it. It's very simple equation, you understand. So find both Lagrangian, Euler-Lagrangian equation of motion and the solution. Okay. Is that okay? These problems?
Yes, sir.
We'll consider other problem also, new problem. Okay, so let us consider mass spring system. Okay, so in one dimensional, suppose I have a spring and it is connected to a mass, and that mass is moving in this. It's one dimensional. So if rest length is L0, so this and suppose this direction is x. You can assume any other direction, and this mass is oscillating in this. So what will be the Lagrangian for this spring constant, say k? So you can write the kinetic energy is one dimensional problem, 1D problem. So no holonomic constant. There may be a non-holonomic constant, but okay. So let me put it for a little bit for charging. I don't know. I charged this battery at the beginning, but that time. Just wait a minute. Okay. Okay. So let me go to. Okay. So this is very simple. Just tell me that what will be the Lagrangian, because this is very simple problem, and you can find the Lagrangian again. Of
सर
just tell me. I'm
सर
actually.
सर इसमें जो काइनेटिक एनर्जी होगा वो हाफ एम एक्स डॉट स्क्वायर ले लेंगे, और जो पोटेंशियल एनर्जी अगर मान लेते हैं मतलब एक्स बराबर जीरो लेंगे इसके, जब नेचुरल लेंथ पे अगर हम लोग एक्स इक्वल्स टू जीरो लेते हैं जहाँ पे उसका नेचुरल लेंथ है, और एक्स
नहीं नहीं,
इलोंगेशन
अब
मान लेते
लाग्रांजियन बताइए। हम बता देते हैं उसमें
हैं हाफ एम एक्स डॉट स्क्वायर जो हो जाएगा काइनेटिक एनर्जी। एक मिनट सर बता रहे हैं सर, हाफ एम एक्स डॉट स्क्वायर प्लस हाफ के एक्स स्क्वायर ले सकते हैं जब एक्स इक्वल्स टू जीरो नेचुरल लेंथ पे लेंगे तो।
हाँ, so this will be half m x dot square. I'm taking that at any time this position is x. This is one dimensional, so position is x, and then the potential energy in a mass spring system. So that you have to add. So potential energy is your k times half k x square, right? What is the half times the spring constant times the elongation square, whatever the elongation that we have to. So elongation you have to calculate. So if that elongation is not x, right? So elongation will be x is the coordinate. Elongation will be x minus L0. Okay. So this is the kinetic energy. This is the kinetic energy. Now potential energy will be half k, then elongation will be x minus L0 whole square. So your Lagrangian will be half m x dot square minus half k x minus L0. If you consider your rest length is 0, then it will be half k x square. And then if you find that if you find this equation of motion, then you can find that simple harmonic oscillator equation of motion. Any question on this? Let me charge my pencil little bit. It's not true. Any question up to this? So are you confident enough? Let me, I found that many people are not present in the class. Let me take attendance today. Okay. So I'll take 2-3 minutes such that this student. So Abhishek Kumar Singh, what is your roll number? Hello, Abhishek Kumar Singh.
Yes sir, 19220 PHY 114.
नहीं आप लास्ट 3 डिजिट बताइए।
114.
114. Then Akhil.
Hello. Yes sir.
बताओ रोल नंबर।
19220 PHY 117.
Everybody just tell me the last 3 digit. PHY कितना है?
117.
Then Ankul.
Mike.
Hello.
Yes sir. Sir 162.
162. ठीक है। आशुतोष 164.
Yes sir. 164.
हाँ। अश्विनी 123.
Yes sir. 123. Yes sir.
Avinash 192. then Ayush Kumar Namdev.
Sir, 124.
124. Diksha.
So 169.
169. Deepak 054. Matt.
Yes, sir. Met 054.
Then Harsh 171. Okay.
Yes, sir.
Manish Maharshi. What is your roll number?
129.
129. Mohammad Yasin.
174, sir.
174. Mukul Misra.
Sir, 130.
130. Pratik, I can get 177. Ranjit Singh.
068.
Math or physics?
सर फिजिक्स P1 बैच से हैं सर.
068. अच्छा, रविकांत
136.
हाँ दिखाई दे रहा है. इसका बाद साक्षी 180. Then
Yes, sir.
Saurabh 139.
Yes, sir.
हाँ. Then Shayan 182.
Yes, sir.
हाँ. Shayantan 141.
Yes, sir.
हाँ. Shambhu
142, sir.
142. Then Shiv Shankar
199, sir.
199. Shruti 183.
Yes, sir.
Shruti Fast Chandal and Shruti Roy.
146.
Shruti Roy 146.
Shruti Roy 146.
Okay, I got it. Then Subham 147.
097.
Yes, sir.
हाँ, Subham Gupta 147. Subham Kumar.
Yes, sir.
094. शुभम कुमार.
094. Then Subham Singh Math 106.
Yes, sir.
Somodeep
150. 150.
हाँ 150. Sujit Kumar नहीं है, वो लॉग इन करके चला गया. सुजीत. देन सुखेंद्र कुमार
097 सर.
097 फिजिक्स.
यस सर.
PHY. हाँ.
Yes, sir.
सुमित
Sir,
सुमित मीना.
099. Sir, 099.
099. ठीक है. वैभव उपाध्याय
Sir, 104.
104. विजेंद्र कुमार
यस सर. PHY 188.
188. गुड. बाकी बच्चों को बता दीजिए कि अटेंडेंस भी होता है, तो वो आ जाएगा क्लास में नेक्स्ट दिन.
हेलो सर.
हाँ
सर, आप सुजीत
हेलो.
कुमार सहगल बोल रहे थे क्या?
आपको 10 बार बुलाया गया और आपको नाम पे ये भी
नहीं
बताया
सर.
कि आप छोड़ दिया इसमें. देखिए
नहीं सर, हम सुन रहे थे आप.
ठीक है, ठीक है.
सर, हम सुन रहे थे सुजीत कुमार, हम सोचे कोई और भी है, इसलिए नहीं बोले.
तो आपका क्लास में और है कि नरेंद्र मोदी है कि अमित शाह है कि अखिलेश है, देख लीजिए, हमारा कैसे पता है. ठीक है, कोई बात नहीं है. आप सुन नहीं रहे क्लास में. बताओ ये काइनेटिक एनर्जी कितना होता है इसका, स्प्रिंग का? सुजीत कुमार बताओ.
सर, हाफ mx डॉट स्क्वायर.
काइनेटिक एनर्जी. और पोटेंशियल एनर्जी
हाफ के x माइनस एल नॉट का होल स्क्वायर.
अच्छा, लिखा है इसमें तो देख लिया. ठीक है, चलो. अगले टाइम से सब बच्चों जब टाइम में बता रहा है, आपको 2 बार पूछा, तीसरा बार हमने बताया कि आप छोड़ के चला गया, मोबाइल पे नहीं है. तीसरे चौथा का कॉल किया, उसका बाद आपका रेस्पॉन्स आ रहा है. ठीक है, चलो ये next we can consider some other problem. Suppose I have a safe like this potential, and this is given. This is my x-axis, this is y-axis, this is some parabolic shape y equal to ax square. So a particle is moving here in this surface, mass m. So what will be the Lagrangian of this system? So this is xy plane. Potential energy, first potential energy I am considering at y equal to at the origin. Potential energy I am considering u equal to 0 at this. चलो सुजीत बताओ क्या इसका काइनेटिक एनर्जी क्या लिखेंगे?
सर हाफ m,
हाँ हाफ m
y डॉट स्क्वायर.
y डॉट स्क्वायर. क्यों
सर? क्योंकि ये सर y डायरेक्शन में मूव कर रहा है.
क्यों की बताना जरूरी नहीं है, आपका फ्रेंड से पूछ लीजिए, सब लोग बता देगा कि आप गलत बता रहे हैं. हमने बताया कि ये मास है, ये मास यहाँ स्लाइड कर रहा है, ये एक इसका इक्वेशन दिया गया है y इक्वल टू एक्स स्क्वायर. हमने पूछा इसका काइनेटिक एनर्जी क्या होगा. गलत है. अच्छा दूसरे से पूछ लेते हैं. विजेंद्र कुमार त्रिपाठी बताओ क्या होगा इसका काइनेटिक एनर्जी?
सर हाफ m x डॉट स्क्वायर प्लस y डॉट स्क्वायर.
हाँ x डॉट स्क्वायर प्लस y डॉट स्क्वायर. लेकिन आपको y डॉट को रिप्लेस करना भी है और लेट मी राइट
y बराबर है x स्क्वायर.
हाँ तो पोटेंशियल एनर्जी, लेट मी राइट पोटेंशियल एनर्जी माइनस mg y. हाँ y इक्वल टू 0 में 0 तो माइनस mg y. नाउ इसको आपको सब्स्टिट्यूट करना है y इक्वल टू a एक्स स्क्वायर से. y इक्वल टू a एक्स स्क्वायर से अगर आप सब्स्टिट्यूट करेंगे तो इससे y डॉट कैलकुलेट कर लीजिए 2a x डॉट. ठीक है ना. तो नाउ यू सब्स्टिट्यूट हाफ m x dot square plus y dot square means 4a x square x dot square, and then minus mg and y आपका हो जाएगा a x square. So it is 1 degrees of freedom because of this particle moves on this parabola shape. So it will be one dimensional. There is only one coordinate x. You have to calculate this, simplify this, but everything in terms of x. So this will be your Lagrangian. Okay. So suppose I have a two mass. You do this problem yourself, connected with a spring. This is m. This is also m. This spring constant k, rest length L0 equal to 0. Suppose. Then this whole thing is released from a height h. Okay. तो दोनों मास को एक h हाइट से ऐसा इस पोजीशन में छोड़ दिया गया. Find the Lagrangian for this. Okay. In next class, tell me what will be this Lagrangian for this. So we have considered many examples on Lagrangian. Now we'll study a little bit more theory, and then we'll come back again. So in next class, Saturday is a holiday, but let us think whether we'll take a class or not. If we release no, in next we'll consider that there is if we have a symmetry in the system, the symmetry we talk about, the homogeneity of space, homogeneity of time, isotropy of space. So if we consider this symmetric, then we told I mentioned that there will be certain quantity conserved because of the cyclic coordinates. So some relation between cyclic coordinate symmetries and conservation. That topic we'll learn in next class. That conservation is related to certain symmetry and cyclic coordinate. Cyclic coordinate I told you, and other things we'll learn. So next few classes we'll consider theory, and then we'll come back again to solving problems. I'll also meantime will give you some problems if you find my problem set. Okay. So any question? Otherwise, we'll stop the class today. Okay, so let me stop the class. Bye bye.